In the vast expanse of the cosmos, humanity has always looked up at the stars with wonder, curiosity, and an insatiable desire to understand our place in the universe. For centuries, we've pushed the boundaries of what's possible, creating ever more sophisticated tools to peer deeper into space and further back in time. Today, we stand at the threshold of a new era in space exploration, made possible by one of the most ambitious and technologically advanced instruments ever conceived: the James Webb Space Telescope. This is not just another telescope. This is humanity's most powerful window into the universe, a marvel of engineering that has already begun to rewrite our understanding of cosmic evolution, planetary formation, and the very origins of everything we see around us. Over the next hour, we'll embark on an extraordinary journey through the cosmos, exploring how the James Webb Space Telescope has revolutionized our understanding of space and fundamentally changed the trajectory of space exploration itself. We'll discover distant galaxies that formed when the universe was just a cosmic infant, witness the birth and death of stars in unprecedented detail, and explore the atmospheric compositions of worlds orbiting distant suns. But this story begins not with the telescope's first images, but with a dream that took nearly 3 decades to realize: the vision and the journey. The story of the James Webb Space Telescope begins in the 1990s, when astronomers and engineers dared to imagine something that seemed almost impossible: a space telescope so large and sensitive that it could observe the universe's first galaxies, formed just a few 100 million years after the Big Bang. This wasn't merely an upgrade to the Hubble Space Telescope, which had already transformed our understanding of the cosmos. This was a complete reimagining of what a space-based observatory could be. The vision was ambitious beyond measure. Engineers proposed a telescope with a primary mirror 6.5 meters in diameter, nearly 3 times larger than Hubble's. But size was just the beginning. This telescope would need to operate at temperatures close to absolute zero, shielded from the sun's heat by a tennis court-sized sunshield consisting of 5 delicate layers, each than human hair. The technological challenges were staggering. The telescope would need to unfold in space like an intricate piece of origami, with hundreds of precise mechanisms working flawlessly in the harsh environment of space. There could be no second chances, no repair missions like those that saved and upgraded Hubble. Development began in earnest in the late 1990s, with NASA partnering with the European Space Agency and the Canadian Space Agency. What was initially called the Next Generation Space Telescope was renamed in 2002 to honor James E. Webb, the NASA administrator who led the agency during the Apollo program. But the path to launch was fraught with challenges. The project faced numerous technical hurdles, budget overruns, and delays that pushed the launch date from 2007 to 2011, then to 2018, and finally to December 2021. Critics questioned whether the project was worth its ballooning cost, which eventually reached nearly $10 billion. The pressure was immense. The telescope had to work perfectly on the first try, deployed 1.5 million kilometers from Earth, 4 times farther than the Moon. At that distance, known as the second Lagrange point, or L2, the telescope would orbit the Sun in sync with Earth, maintaining a stable position relative to both celestial bodies. On December 25, 2021, Christmas morning, the James Webb Space Telescope finally lifted off from French Guiana aboard an Ariane 5 rocket. The world held its breath as humanity's most expensive and complex space observatory began its month-long journey to its destination. What happened next was nothing short of miraculous. Over the course of 2 weeks, the James Webb Space Telescope executed what NASA called the most complex sequence of deployments ever attempted in space. First came the deployment of the solar array, providing power to the spacecraft. Then, piece by piece, the telescope began to unfold. The forward and aft sunshield pallets extended, followed by the deployment of the sunshield membranes themselves. Each layer had to be tensioned precisely, creating the multi-layered barrier that would protect the telescope's instruments from the sun's heat. The tension was palpable in mission control rooms around the world. Each deployment was a single point of failure that could have ended the mission before it truly began. But one by one, each mechanism worked flawlessly. The secondary mirror deployed on a telescoping boom, positioning itself precisely in front of the primary mirror. Then came perhaps the most critical moment, the unfolding of the primary mirror's wing segments. These two side panels, each containing 3 hexagonal mirror segments, had to rotate into position with extraordinary precision. When the final mirror segment locked into place, the telescope had transformed from a compact, folded package into a gleaming golden-eye giant ready to peer into the cosmos. But deployment was only the beginning. Over the following months, engineers began the meticulous process of aligning the telescope's 18 hexagonal mirror segments. Each segment, made of beryllium and coated with a microscopically thin layer of gold, had to be positioned with nanometer precision to function as a single, perfect mirror. Using a process called phasing, engineers adjusted each mirror segment using tiny actuators, gradually bringing the telescope into focus. The process was like tuning 18 separate telescopes to work as one, a feat of engineering precision that pushed the boundaries of what was thought possible. Meanwhile, the telescope's instruments underwent their own commissioning process, the near-infrared camera, or NIR cam, which would serve as the telescope's primary imager, the near-infrared spectrograph, NIR spec, designed to analyze the chemical composition of distant objects, the mid-infrared instrument, MIRI, capable of detecting the faintest heat signatures from across the cosmos, and the fine guidance sensor and near-infrared imager and slitless spectrograph, provided by the Canadian Space Agency. By July 2022, after 6 months of careful preparation, the James Webb Space Telescope was ready to begin its mission of discovery. First light and revolutionary discoveries. On July 12, 2022, the world witnessed something extraordinary. NASA released the first full-color scientific images from the James Webb Space Telescope, and instantly, our perspective on the universe changed forever. The first image revealed was Webb's Deep Field, a view of galaxy cluster SMACS 0723 as it appeared 4.6 billion years ago. But this wasn't just another pretty picture from space. This single image contained more detail and revealed more distant galaxies than any previous observation in human history. What made this image revolutionary wasn't just its beauty, but what it represented. In capturing light that had traveled for over 13 billion years, Webb was literally looking back in time, showing us galaxies as they appeared when the universe was just a few 100 million years old, cosmic infants in the grand timeline of existence. But the Deep Field was just the beginning. The initial release included 4 other targets that showcased Webb's extraordinary capabilities across different types of cosmic phenomena. The Carina Nebula, a star-forming region 7,600 light-years away, appeared in unprecedented detail. Webb's infrared vision pierced through the cosmic dust that obscures visible light, revealing baby stars in the process of formation, stellar nurseries where new suns are born from collapsing clouds of gas and dust. For the first time, astronomers could see the very earliest stages of stellar birth, watching as gravitational forces sculpt the raw materials of space into the nuclear furnaces that will shine for billions of years. The level of detail was staggering. Individual protostars, previously hidden from view, suddenly became visible, their surrounding disks of material captured with crystal clarity. Then came the observations of exoplanets, worlds orbiting distant stars. Webb's first exoplanet observation targeted WASP 96b, a gas giant located 1,150 light-years away. But Webb didn't just see this distant world. It analyzed its atmosphere in extraordinary detail. By observing the planet as it passed in front of its host star, Webb detected the unique spectral signatures of water vapor, clouds, and atmospheric haze. This wasn't just detection. This was detailed atmospheric analysis of a world orbiting another star, opening up entirely new possibilities for studying potentially habitable worlds. The implications were staggering. If Webb could analyze the atmosphere of a gas giant in such detail, what might it reveal about smaller rocky planets more similar to Earth? The search for signs of life beyond our solar system had suddenly taken a giant leap forward. Webb also turned its attention to the death of stars, capturing the Southern Ring Nebula in unprecedented detail. This planetary nebula, formed when a dying star expelled its outer layers, revealed intricate structures and a complex history that had been invisible to previous telescopes. The images showed not one, but two stars at the nebula's center, revealing that stellar death can be far more complex than previously understood. The nebula's shells and filaments told a story of stellar evolution that spanned thousands of years, each layer representing a different phase in the star's final act. Perhaps most remarkably, Webb captured Stephan's Quintet, a group of 5 galaxies engaged in a cosmic dance of gravitational interaction. The level of detail revealed shock waves, tidal tails, and star formation triggered by galactic collisions, showing how galaxies grow and evolve through cosmic encounters. These first images weren't just scientifically revolutionary, they were emotionally transformative. People around the world found themselves staring at images that revealed the universe in ways they had never imagined possible. Looking deeper into cosmic history, as Webb continued its observations throughout 2022 and into 2023, each new discovery seemed to rewrite textbooks and challenge our fundamental understanding of cosmic evolution. One of Webb's most significant contributions has been its ability to observe the most distant galaxies ever detected. Galaxies that formed when the universe was less than 400 million years old. These observations have revealed something unexpected. The early universe was far more active and complex than astronomers had predicted. Traditional models suggested that the first galaxies should be small, simple structures, gradually growing larger and more complex over cosmic time. But Webb's observations revealed massive, surprisingly mature galaxies existing much earlier than theory predicted. Some of these ancient galaxies appear to contain supermassive black holes with masses billions of times that of our Sun. This discovery poses a fundamental question. How did such massive black holes form so quickly after the Big Bang? The answer could reshape our understanding of how the universe's first structures formed. Webb has also provided unprecedented insights into the cosmic dark ages. The period between the formation of the cosmic microwave background radiation and the ignition of the first stars. During this era, the universe was filled with neutral hydrogen gas, opaque to visible light, but transparent to infrared radiation. By observing in the infrared, Webb can peer through this cosmic fog, revealing the moment when the first stars began to shine and ionize the surrounding hydrogen. This period, known as the Epoch of Reionization, represents one of the most significant phase transitions in cosmic history. The telescope's observations have shown that this reionization process was more complex and varied than previously thought. Rather than occurring uniformly throughout the universe, it appears to have happened in patches, with some regions clearing before others, creating a cosmic Swiss cheese pattern of ionized and neutral regions. These discoveries have profound implications for our understanding of cosmic evolution. They suggest that the early universe was a more dynamic and varied place than we had imagined, with significant regional differences in star formation and galactic development. Webb has also revolutionized our understanding of stellar nurseries, the regions where new stars are born. By peering through the dust that typically obscures these regions from visible light telescopes, Webb has revealed the intricate processes of star formation in unprecedented detail. In the Eagle Nebula, Webb captured images of stellar nurseries that showed individual stars in various stages of formation. Some were still embedded in their natal cocoons of dust and gas, while others had begun to clear away their surrounding material, revealing the newly formed stars within. The telescope has observed brown dwarfs, objects too massive to be planets but too small to sustain nuclear fusion like true stars. These failed stars provide crucial insights into the lower limits of star formation and the boundary between stellar and planetary formation processes. Perhaps most remarkably, Webb has begun to observe the formation of planetary systems around young stars. The telescope can detect protoplanetary disks, the rotating disks of material from which planets form, with such clarity that astronomers can see gaps and structures that indicate planet formation is already underway. These observations are providing the first direct evidence of how planetary systems like our own solar system form and evolve, offering insights that could help us understand how common Earth-like worlds might be throughout the galaxy. The atmospheric revolution. Perhaps no area of astronomy has been more transformed by the James Webb Space Telescope than the study of exoplanet atmospheres. In just its first year of operation, Webb has analyzed the atmospheres of dozens of worlds orbiting distant stars, revealing details that were previously impossible to obtain. The precision of Webb's atmospheric analysis is truly remarkable. By observing the slight dimming of starlight as a planet passes in front of its host star, Webb can detect the spectral signatures of specific molecules in the planet's atmosphere. Different molecules absorb different wavelengths of light, creating unique fingerprints that Webb can detect and analyze. This process, known as triggered star formation, helps explain how star formation can occur in waves throughout a galaxy, with each generation of massive stars helping to ignite the next. The telescope has also provided unprecedented views of stellar death. When stars like our Sun reach the end of their lives, they shed their outer layers, creating beautiful planetary nebulae. Webb's observations of these nebulae have revealed intricate structures and complex chemical compositions that tell the story of stellar evolution. The Ring Nebula, one of the most famous planetary nebulae, appears completely transformed when viewed through Webb's infrared eyes. The telescope revealed a complex, three-dimensional structure, with knots, filaments, and shells of material ejected at different times during the star's death throes. These observations are providing new insights into how dying stars enrich the interstellar medium with heavy elements, the building blocks of planets and life. Every atom in our bodies, except for hydrogen and helium, was forged in the nuclear furnaces of stars and dispersed into space when those stars died. Webb has also observed the most violent stellar deaths, supernovae and their aftermath. When massive stars explode, they release more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. The telescope's observations of supernova remnants have revealed how these explosions create and disperse the heavy elements essential for planet formation and life. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 AD, shows intricate filamentary structures where shocked gas glows at different temperatures and densities. Perhaps most remarkably, Webb has begun to observe the immediate aftermath of stellar explosions, capturing the expanding shock waves as they interact with the surrounding interstellar medium. These observations are providing new insights into how supernovae trigger star formation and shape the structure of galaxies. The telescope has also studied neutron stars, the ultra-dense remnants left behind when massive stars explode. These objects pack more mass than our Sun into a sphere just 20 kilometers across, creating gravitational fields so intense that they warp space and time itself. Webb's infrared capabilities have allowed it to study the environments around neutron stars, revealing how these exotic objects heat and ionize their surroundings, creating glowing nebulae powered by the neutron star's intense magnetic field and rapid rotation. Galactic evolution and cosmic architecture. The James Webb Space Telescope has fundamentally changed our understanding of how galaxies form, grow, and evolve throughout cosmic history. Its ability to observe the most distant galaxies ever detected has revealed that the early universe was far more complex and active than astronomers had predicted. Traditional models of galactic evolution suggested that the first galaxies should be small, irregular structures that gradually merged and grew into the large, organized galaxies we see today. But Webb's observations have challenged this view, revealing surprisingly massive and mature galaxies existing when the universe was less than 1 billion years old. Some of these ancient galaxies appeared to contain as much mass as the Milky Way, despite forming when the universe was just a fraction of its current age. This discovery has forced astronomers to reconsider how quickly galaxies can assemble mass and develop complex structures. Webb has also revealed that supermassive black holes, objects millions or billions of times more massive than our Sun, existed much earlier in cosmic history than previously thought. These black holes appear to have grown to enormous sizes remarkably quickly, challenging our understanding of black hole formation and growth. The relationship between galaxies and their central black holes is one of the most important discoveries in modern astronomy. Webb's observations suggest that this relationship was established very early in cosmic history, with black holes and their host galaxies growing together in a complex dance of mutual influence. The telescope has also provided new insights into galactic mergers, the process by which smaller galaxies combine to form larger ones. Webb's observations of Stephan's quintet, a group of interacting galaxies, revealed the complex dynamics of galactic encounters in unprecedented detail. During galactic mergers, gravitational forces can trigger intense bursts of star formation, reshape galactic structures, and feed material into central black holes. These processes can completely transform the participating galaxies, turning spiral galaxies into elliptical ones and creating some of the most spectacular phenomena in the universe.